Okay. Projection is not really optimal, but not too bad. Today we'll look at database design. Particularly, we're going to consider MySQL. Um, the database models uh, was considered, uh, I think, a little after the World War II, 1960s, 50s. Flat database models, file-based. File-based database service still the majority. Most of why? Because almost all the web pages are simply file-based. But there are much more other type of data. If they are security sensitive, then usually, and also if they need critical user service, user request, and response to user request, then data may be stored in a database, more formal database. So database models, once first looked at the concept of a network and then hierarchy. And then since a little earlier than 1980s, the relational database model was discussed a lot. And then from 1980s, relational database systems has been popular and functional and reliable so far, although we have a little bit of the technology evolved to object relational database model, but object relational database model is not much different from relational database models. Relational database models are strong enough to use and so robust, resilience, and improved its functionalities and securities, serviceabilities a lot, and very easy to use. Although we are thinking over here a little bit of a weakness, multi-valued attributes cannot be served. What is a multi-valued attributes? Kevin, do you can you imagine what it would be? Multi-valued attribute. For example, if some student table, think about the table. Student table, then there is student can be structured and described over multiple attributes associated with the students. So maybe student name, student ID, and then when it comes to phone number, then there are many students who might have more than one phone numbers, right? If a student works at for the company, then there's another number for landed line for the company. If you have another landed line at home, then you have another phone number, and you have another number that you can carry all the time for your cell phones. And some students might have more than one cell phones. And also, those who guys worked very important missions at work, then they have their own cell phone, and cell phones provided by the company, right? My daughter has two phones. One, her own personal, and the other one's from, yeah, she's worked for the government, federal government. But anyway, multi-valued. Multi-valued cannot be represented in a table. Think about the columns. Then you have a phone, then is one column. Are you going to make another column for second phone and another column for third phones? You could do that, but many of us do not have even second phones. Only one phone is enough, right? It's not really ideal. It's not really efficient to represent. If somebody has one phone, somebody has more phones, how can we represent that in one single frame? We cannot do that in the form of a table, right? But relational database is nothing but a table forms. It has columns and rows. So that is a weakness of relational database models. Another weakness for representation aspects, that is a composite values. What do you think of the composite values? What kind of attributes may be composite values? Think about the student table. Kevin, what do you think of the composite attributes? Let me say you can pick one. Name, CWID, home address, phone number. Phone number we already talked about. That is a multi-valued. And GPA, maybe advisor. Okay, so far. Which one would be the composite value? I think CWID is an atomic value, one number only, right? Composite value means if we say address, then there is a street, city, state, zip code, country. We can split address into several different components, and at the same time, we can compose all of them to say, hey, this is an address, right? So composite value is, we can just describe a whole mailing address, then that is a composite value. But at some other time, for a special purpose, if you want to, for example, data analysis, they want to see, hey, how many people are from New York State? Then they can collect by the state, right? NY, they collect all the address, all the people who has NY in that address. For that purpose, then we might have another columns. City, state, zip code, streets, country. They can be all separate attributes. But at the same time, those separate different attributes needs to be composed together to present, right? Hey, this is my address. So it is not really simple if we still consider a table for the representation about composite attributes. But those multi-valued composite attributes can be represented in object-oriented database models. Object-oriented. We're not talking about the object-oriented data model here because we have only 3 sessions, right? We have to move quickly. I want to move as quickly as I can. Therefore, we may have spent more time on coding. Kevin, you're not really the issue because you already learned, you already completed 131, 231. You may be okay, but other students from other background for the master's program directly, then they might have some issues. Therefore, I want to spend more time on coding. Okay. So object-oriented, but what is the strength of relational database models? Strength, I believe, points there only the weakness. What is the strength then? Is there no strength for relational database models? Of course, there is a strength, which is SQL, right? Because Kevin already took the undergraduate database course, so SQL statements. SQL statements, what do you think? SQL, if you compare SQL statements and Python, which one's simple? SQL statements is a lot simpler than Python, right? SQL statements simply say what we want. If we describe what we want, do you think we definitely get that one without saying how to get? It's not, right? It's very hard. We need to have not only what we want, we need to describe it not only what we want, but also how we get it, right? Pythons, we have to take care of both what we want to do, how we want to do, how we can do, right? But SQL statements, simply what we want. All the methods, all the algorithmic procedures are left onto DBMS only. So database management systems can do. In our case, MySQL can do. We don't have to worry about. So that is much, much simpler. That is the strength for relational database models. That is the strength. The reason that we want to consider object-oriented database model is because we want to fix the weakness of a relational database model. Weakness. So we successfully made it by using object-oriented database models. But because object-oriented database model represent a very, very complicated real-world structure, SQL expression is not enough to describe what we want because it is so complicated. Along that way, many researchers now try to develop another language stemming from SQL. So they developed by adding more functionalities into the language more and more. And while they were discussing about that in early 1990s, finally they thought, this language is so complicated. We cannot see anything like SQL for object-oriented database. So they have now, we have another weakness if we have object-oriented database. So which weakness is more problem than the strength? So they think, hey, let's go back to relational database. Relational database is much easier and simpler. Therefore, you know what? Computer is not really dealing with a complex problem. Computers can do only simple problems better. The strength of computer processing is not to solve complex problem solving, but to solve massive data. Even if I have millions, billions of data, if we have one simple the code, then you can deal with the billions of data very, very quickly. That is the strength of computers. Therefore, a relational database, if it runs on computer, then hey, we need to make our model simple. So simple model is fitting in the computer. So they now go back to relational database, and while keeping the strength of object-oriented database, so they developed new model, which is object relational database models. Object relational database models uses still SQL. Simple language. Very good, right? Object relational database model can do still complicated real-world database, real-world structure. So it can handle multi-valued, it can handle composite values, but it can be accessed by SQL. Therefore, object relational database model is now the winner so far for the past 20 years, since 2000 years. But main idea for object relational database is still relational database. So we'll look at relational database. The concept of a relational database is to start with the schema. What is a schema? Schema is a structure of database, right? Structure information. Relation is nothing but a table. So relation and relationships in relational database are not the same. Relation, the terminology relation in relational database means simply a table. Nothing more than that. So relation is, this is a table. There's a relation. Relationship. This is a literally relationship. If we have two tables like this is table 1. So we have columns and rows. We have another table here. So we have columns and rows also. If you consider the spreadsheet or Excel files, let's say you have two different Excel files. Is there some relationships? Systematic relationships? There's no relationships, right? How can you make them connected? How can you make these two tables connected? That's the main point of a relational database. So relation is a table. Relationship is real relationship. Relationship of the each object here, another record here. I want to relate this with some other object in another table. How can we make them connected? We can make them connected by sharing, say this value and that value are the same, then they are connected, right? For example, this is your student table. So you have a CWID. Let's say you have a CWID here, your name, your major, GPA, and then finally there is this sensitive data, your social security number here. And this is your tax table, okay, IRS information. So there is IRS information can be identified by your social security number, right? So there's a social security number, your name, your income, your expense, and finally whatever the tax amounts and whatever the amounts the withheld from your the salaries and all those informations there. So if IRS wants to combine the student table and their IRS table together, then they can connect for special relationships by having this. We have social security number in the student table and social security number in IRS tables, so that by having these two, by having the same columns, by having the same column, then we can say, hey, this guy is appearing here, that guy. This student paid the tax, that amount of money. And if we see another student here, social security number, and there are the two numbers are the same, so this student appears in our table, IRS table here. And some other student table here, that the social security number does not have it here, then IRS say, hey, this guy didn't file. Or maybe this student is too young to file, or this student is too young, then they should not. Right. You see the relationship and relations, right? Two different things. So they are not the same. Significantly different, not the similar. In English, they are similar, but in relational database technologies, they are quite different. Okay, we have two different schemas here. Relation schema and database schema. What did I say schema here? Schema is a structure, right? Or definition. Relationship is nothing but based on the common attribute. Based on the common attribute, there is a relationship. Schema is a structure. Therefore, if we say relation schema, then that is what kind of structure? If we say relation schema, then that is the structure of table, because relation is nothing but the table. So relation schema is the structure about a table. How can we describe the structure of a table. Simply we say this table and that table are not the same based upon what? Yeah, columns, attributes. So relation schema is nothing but the set of attributes. Set of attributes. That is a relation schema. What is a database schema then? What is the relation? What is the difference between relation and database? Relation is a bigger concept. Relation is nothing but a collection of relations, right? So database schema is nothing but set of a relation schema. Set of a relation schema. So now clearly understands what they are talking about. So understanding the concepts, and by understanding the concepts, we may be able to see, and you can explain some terminologies. So this is an example. Database schema, which is not of nothing but a set of relation schemas. Relation schema is nothing but a set of attributes with their types as well, if we want. So student is student table. Student table is a CWID. This is an attribute name, followed by type. We can say CWID integer, and CWID is a name, which is a text. Text is not the formal type standardized in database community, but in real software packages like MySQL or Oracle, they developed sugar-like type, so we taste better. Unless otherwise we say simply text, then we need to say character. What is the size of a character? 13 characters. Or we can say variable character, varchar, minimum 15 characters. We should say that, right? So student name, if we say varchar 15, then why only student's name is 15 characters? Why not 25 characters? Why not, in my case, 4 characters? Short, right? Somebody has 2 characters. Not homogeneous, right? So there is some issue. Hey, rather than we strictly define the type with the number of characters, can we simply leave it on the computer itself? So computer can allocate the size as needed, as available, right? So that is called the text. So text is nothing but number of characters or variable number of characters, which means the type that is char character, char 13, or varchar variable character, we can say 12. If we say char character, then fixed, always 13. If we say varchar, 12, every 12, if it is over 12, then double it, 24. Okay, that is a varchar. Text is up to the computer. So as a database designer, I want to be free from that all details. So simply say text. Age integer, major in text. Department, department name. So department name here is very similar is nothing but major of students. What is your major? Cybersecurity. What is the department? Cybersecurity, right? So how do you know which students in what department? We can see because by looking at major in the student table, we know what department that students belong to, right? That is the relationships between student and department. We have relationships. These relationships can be formed based on common attributes. Major in student table is the same as name in the department table. How do you know they are the same common attributes? If we know the values, right? What is a major? Cybersecurity. What is a major? What is the department name? Cybersecurity. Then they are the common. They are really strictly common. If we think of the enroll here, enroll table, then we have a faculty. No. Enroll should not with the faculty. Enroll should with the CRN. So here at CRN, so we have an integer here. So student can register a specific course, CRN here. Actually, this is not a course. Maybe this is a class, right? So students register and register a specific class. So we have a CRN number and student CWID number. By having those two pairing, we know, hey, this student is in that class, and the same students also in another class, second class or third class. So we can see that. There's another table called the faculty. Faculty has a faculty name, and the faculty has affiliated department, so DEPT. DEPT in the faculty table is the same as the department name in department table, right? The course and course title, CRN number, and credit informations, those are there. Two things that I want to point out here: primary key and foreign key. Primary key is a set of attributes that can identify one record from another records. For example, student table. If we see student table, then which may be the key? We simply know because that is a CWID number. In the table of a student, there's no two records which have the same CWID, right? Only if there's one CWID, then one record only. So that is called the primary key. By knowing primary key, we can point specifically one record in the given table. That is a primary key. Foreign key is a little different. Foreign key related with the relationships. For example, here, student and department. Student major here, let's say cybersecurity. And department name, cybersecurity. Cybersecurity in department is the primary key for that department table, right? So by knowing that department name, then we know there is a unique one department. There's no two departments having the same department name. That is the primary key. That primary key may appear in another table, like here, major. So the students take that department. They are sharing the same number, same value. But major in the students is not the key in the student table itself. But if we see the root of these attributes, this attribute comes from where? Department, right? Department first existed. Therefore, students take that department. It's not the case that because students take specific field, therefore department is created. It's not like that, right? Department first created, so that is a primary key there. And if you want to take that department, then I can borrow that value, we can say that, hey, that is my major. That is a foreign key. So which one is foreign key? Name is a foreign key or major is a foreign key? Major is a foreign key. This is a foreign key. Name in its own department, then this is primary key. Right? This is a primary key and this is a foreign key. Major in student is kind of a foreigner, right? So foreigner, but its origins is in the department. Same thing here, enroll. Student ID is not really associated with the enrollment table. Student ID is originally from where? Student table, right? Originally from student table. So this student ID here is a foreign key. That CWID in the student table, that is a primary key. Okay, so we need to practice that a little later. So we want to design a database, conceptual design. What is a conceptual design? Then we can think of the way that we analyze the real world application. Then we need to design the tool that we want to use to design conceptually are available. The one most popular tools that we use is entity relationship model. We call that ERD. Entity relationship models. Logical design. So once we have a conceptual design, then next step is logical design. Outcome of a conceptual design is ERD. Outcome of a logical design is relation schema. So we need to have a set of attributes with the type. Therefore, we can define a table in a real real database management systems. In our case, MySQL. After that, we can implement it. Because we have a ER diagram to relational schema, from relational schema to here, define database. Once we define database, then we can define table. And therefore, we can insert data, which is a populating the data. Meanwhile, we made to do a physical design, retrieving data. And then once we have this, then we have retrieving data. In order to retrieve data more efficiently, then we can make a physical design. Okay. What are we going to do in this class? This is not database system only, right? This is a database system. We cover only 2-3 sessions. We don't cover all of this. Even here, user interface. This is the next step. We are not going to do all of this. We need to simplify this for our practice. Conceptual design, the output from the conceptual design is a ER diagram. This is kind of ER diagrams. You learned the ER diagram, right, Kevin?
Yes.
Right. So what is a diamond? What is the rectangle?
I believe the diamond is the table. The rectangles are the attributes.
Not really. rectangle can become a table, but I didn't put here circle. Student has a number of circles. Circle is a attributes. So student has a CWID and name, major, and course has a course title, CRN number for simplify, and then maybe credits. And relationship is a real relationship, like common attribute. We share the common attributes. In this case, so table can be, a rectangle can be a table. When you do from conceptual design to logical design, right? That's what we want to do. If we have in the conceptual design, which is a ER diagram, if there is a rectangle, then that is nothing but a table. If there is a circle, it's nothing but the attributes to that table. Attributes. What about diamond? Some diamond can be table. Some diamond simply share the common attributes. Okay. So either it can be converted to a table, or it can be simply sharing common attributes. That is logical design. So if we see the top first ER diagram, then we see two tables: students, course, and grade. Grade will become a transcript. Student is student table, course is course table. Takes, in this case, is there any attribute that we can share? Therefore, it could be major can appear in course, or course appear in students. In any case, it is not really efficient at all. Therefore, in this case, table will become another, diamond will become another table. We call that enrollment in this case. So we can see this enroll. And we can share one attribute from here, so that we CWID. CWID comes from here. And another attribute needs to be shared, like CRN number. CRN number comes from here. So by borrowing attributes from both sides, CWID from student table, CRN from course table, put two attributes into one table, and we make that as one separate table. That is the case here, number one. Diamond can become a table. In another case here, student and transcript admin. Students, this second ER diagram explains how diamond can play. Is there only one relationship for given two rectangulars? In other words, only one relationship if we have two tables? Or could it be more than one relationships? Could be more than one relationships, right? Let's say if you have a transcript. Then student can request the transcript. And admin, different attributes, different table can view the transcript. Or the other, admin can update transcript. Different roles of relationships, right? Not only view, but maybe updates. That is also possible, right? Not only one, but also more than one, right? Let's say update. In this case, student is a table, like a logical design. Then this is a table. This will become a table. Transcript is a table. But request may not be a separate table, but share. For example, this student maybe in this case, that is another separate tables. That's a better request. In what case we can do one? That is the case. It's not here. If we have a department, for example, I want to make here. Well, I already said here, right? CWID students and transcript. We have CWID. Major transcript. CRN. This is not really good enough. But if we have a department, student has, for example, let's say this is the department. We have a diamond here. This diamond cannot be its own separate table. This diamond can be disappear. Therefore, as I said here, diamond can be a table, or diamond itself disappear. Instead, there may be common attributes. That's what we have here. Student has let's say CWID student itself and name and phone number. We have a department here. Department has a department name and department chair. So table of students. This is a student. We have here CWID. Student name and student phone number. And here we have a department. So department. So this is a department. Department is a rectangular. Student is another rectangular. So they can be a table. Student has department has a department name and department chair. Okay. Now, if we see this department and student, there's no common attributes. Still, we have here diamond. Diamond means there is a relationships. What kind of relationships between student and department? There's a major, right? So we need to have a major here. And by the way, this major is nothing but department name. So department name is department name in the department. That is department's hometown. But the value can be migrated to the student table. Therefore, foreign key here, right? Student value cybersecurity is a foreign key to student itself. Because student primary key for student is CWID. By sharing this major and name, this diamond disappeared. Therefore, finally, in relational database, in logical design, we share department name and student major. They are the same values. That's a logical design. So logical design is the process, conversion process from ER diagram to relation schema. And then we need to do implementation, real implementation. Here we need to practice, okay? We are going to use DDL, data definition language. Okay, so we need to create database, this database. Once we have a database created, then we create table, things like that. But before we do, we need to create a user. Okay, so let's try to do that. Okay, Kevin, you can open up your terminal. You can make terminal. If yours is Windows, then there's a Windows button. Windows button, right? Holding the Windows button and hit R button, and there you type CMD, right? Then command line terminal appears. So you have the similar terminals appears.
Can we go to the terminal or MySQL?
Terminal. Okay. So you need to find out the location of your MySQL software. In my case, USL local CD change directory USL local. Then I can see MySQL /9.0.1. That's new version. Do you need help? This is not Windows. You have different. Right. I think into. There's an MySQL somewhere here, so you can do MySQL -u root -p, and you can put your root password. So did you get in your MySQL?
Yeah.
Okay. So for the Windows users, the file location is not USL local. This is Linux file structure, system. The Windows file system is not like Linux, so it is a C:\/ program space files / MySQL /MySQL space server, whatever the version / bin for binary directory. If you get in there, then you will be able to see MySQL. Same thing here for the Mac users. I need to go further. So MySQL -9.0. something, and then cd bin. There's a bin directory here. If I type pw print work directory, then it comes from USL /local /MySQL -9.0.1 Mac OS 14 ARM 64 bin directory finally. So if you say here, then we will have a MySQL. So MySQL for Mac users, if you say MySQL, then it's not going to work because we didn't put any the path availability here. So you need to start with the dot slash MySQL and -u root -p. Then you will ask you to enter your password. Then you will have a MySQL prompt. Here we want to create our user login. Okay, first, so create user slash jyun at jyun and then open quote and close quote, followed by @ another open quote, localhost close quote space identified by, and then you need to put your password. In order not to forget, my case, I use the same login ID and same password. I know this is not ideal way for cybersecurity professionals to use, right? But if I create my difficult password for this database login, then tomorrow I forget it. So I have in big trouble. I'm in big trouble. So I want to use the same ones. And also this database, MySQL, running on my laptop only. This is my own. So no one is accessing. So I'm using jyun. Okay. And then usually for database command end with a semicolon. Unless otherwise, this database command still waiting for you to complete the expression. So semicolon is the delimiter of your command. Depending upon some software, sometimes not really needed, but most of SQL expression you need to have semicolon. Okay, in this case, I'm not sure this is without semicolon whether it works. So let's try if it works. If it works, works. If it's not, then we need to put the semicolon at the end. Because it waits until I enter semicolon. Anytime if I enter semicolon, this MySQL engine now understand that is the completion of the command and therefore process it from that time. So hit enter here, then it says query okay, 0 rows affected. What that means is not yet, right? Let's see. And here, another command that you can see here, show databases. Show databases, hit enter. Still waiting for me to the semicolon, so I put semicolon. So we have those databases available. So we want to create the database. So I want to do create database and database name. What do you want to do database here? Let's say 505 DB. Semicolon and enter. And then show database. Semicolon, then you may be able to see there is a table name appears in that table, right? Not table name, database name. 505 DB, that is a database name. Now we have one database, we have a user. Then you need to do, hey, I want to grant all privileges on, if we do star.star, what that means is that star means all the database. First star means all the database. Second star means all the table. If you want to specify that a particular 505 database only, then you need to say 505. But if you want to do, hey, I want to do only entire, mainly because this time, this class database session is very, very, very limited. We don't do much about. We simply taste a little bit of the way that we can handle MySQL DBMS. So let's make it simple. If we want to make a different privileges on different tables, different database, different tables, so much uh, uh, different level of privileges assigned to user, then eventually we also may be complicated. Okay, so we have only 2-3 sessions, so make it simple. That way we don't forget. So we want to give all the privileges, all the database, all the table to Jaeyun at local host semicolon. Hit enter. Okay, and then let's quit, and let's come back. In this case, put rather than root Jaeyun. Did you make it Jaeyun in your case or your name K? Right, you have to do that. Some students follows mine, so I have so many Jaeyun accounts. My students MySQL. So there, put yours. See if you can get in. Are you in your? Did you get it? Did you get that prompt, MySQL? You need to have this. MySQL space -u space Kevin whatever space -p, then enter the password that you created.
No, it's saying that page is not recognized as an internal external.
What is it? It's after we get into MySQL. Okay. Now we want to see if we can create my database. Let's see. What we want to do, well, we want to create some of it here. Okay. So let's look at student table. So create table student CWID integer name text age integer major. Actually in this case because major is a foreign key, then we need to define department name first, right? So whatever the value appears in major, then that is affected by the department. So what we need to do, we need to define department first. So department, we have name text, chair text, and then primary key is name, and then semicolon. Oh, we have to select a database. Show databases 505 DB, right? We are not going to make a table for entire database. We need to pick one database. The way that we can pick one database is command like this. We need to use 505 DB. We need to use use. We need to use the command use to pick a specific database. There we can do create table, department, name and chair. We can specify primary key also. Name is used to key specified without a key length. Okay, so if we say key length as it asks us, then we need to do here varchar. Rather than use text, we need to say varchar, let's say 5. Let's put longer than that, 10. and then primary key name, and hit enter. So table is created. So in this case, we need to see show tables. Then one table is created. Okay, show tables. If we want to see the schema of that table, then schema of the schema relation schema, then we need to see describe and department. Semicolon, then we can see the schema. So we have two field name and chair. Type of name is varchar, 10 character. Type of chair, simply text. If we see this name, then it says here, is this a key? Then it says the PRI. Yes, it is a primary key. Okay, because this is a primary key, will there be a null value for name? No, null value is not available. Chair, so department name should exist, right? Is there any department where there is no name? That's so clearly they all make sense here, right? What about chair? Sometimes chair position may be vacant, right? That's possible. Some department currently no chair. So null value, yes, possible. Key, no, it's not key. Is there any default value? No. Default value is null. Null itself is a value. And what it means is that null, meaning nothing. Okay. So we can create more table. Create table student CWID, integer, and name, text, age, integer, major. Here's a very careful. This major is a foreign key, so type should be the same, exactly the same. Although I put here text, because here when I create the department with the primary key name, this guy says name used in a key specification without a key length, then there is an error. So we need to put the key length. So instead of name text, I put here name varchar 10. That varchar 10 is the same here, varchar 10. After that, hit enter. Then because we didn't put any semicolon, still we can continue to add. So we have, for student, we have a CWID, name, age, and major, 4 attributes there. We need to put here primary key. Primary key is a CWID. And then foreign key. Foreign key is a major. And then we need to say, if it is a foreign key, then we need to specify which one is its primary key. What is his original location? Then we need to say here, references, and then department of name. I believe this is a syntax. If there's a syntax error, then we will fix it. Hit enter. Oh, luckily there's no error. So we need to say right now see tables. I have 2 tables. Description of student, semicolon, description of department. Then now I see CWID is a primary key for the table, and major MUL. MUL means mutual, not the primary but mutual. Mutual means here itself is a foreign key, but its original location here is that is a primary key. That mutual connections appear in another table, another location here. We don't see it. You may be able to see it, but right now, let's say that it's not. So we did, we create database, we create tables. Now we need to populate the data. So insert into, we need to populate the department first. If we want to populate the students, let's see what happens. Students, values, we need to put student ID 1111 and name Kevin, age 19, major cyber. That's what I want to create for Kevin. And that data is supposed to be in the table students. So far so good. See what happens. If I hit enter, definitely there is an error. What kind of error that we would have? The major cyber, that's a foreign key. If it is a foreign key, it implies that the value itself should first exist its own location. We didn't create the department, cyber department, but we want to create. What that means is that we don't have the department cyber, but we admit students who wants to study cyber. That doesn't make sense, right? Therefore, this database should say that. If I hit enter, then this database says that. Right? It says cannot add or update child row. Child row means this particular row. A foreign key constraints failed. Didn't explain much, but what it means is just what I explained. So what you need to do is you need to insert the department first. Department values and department major, department name is cyber. And then department chair Chen and close and semicolon. In this case, would there be a similar error or would it be okay? Okay. Oh, okay. Good. After that, I want to bring up the previous tuple for student about Kevin. See what happens? Oh, good. So if I do select star from department, I have one department information. Select star from student, I have one students. Right? Okay. We can go further, but I think what I am going to do, I am going to ask you to create and populate all the data till next week. Therefore, we can do SQL more. If we do this, then longer time that we have to insert, to create another table. That is good for you to do the homeworks. All right, so homework will be, I want to create faculty table, enroll table, course tables with the proper primary key and foreign key. One correction here is the enroll. The first attribute should be CRN, type integer like this, and student int, and student here stud in enrollment is nothing but CWID in students. So stud in enrollment, that is a foreign key. References CWID in students. For simplicity, don't make this a foreign key. Okay, in this case, otherwise it'll be really no foreign key in this case. For our lab simplicity, lab will be complicated if we make a foreign key here, foreign key there, then we have to insert and deletions, all very complicated. But primary key, here we need to do primary key. Foreign key, primary key we already did. Faculty name, so no foreign key, no primary key here. Course, I would say no foreign key, no primary key. Faculty, this is primary key. DPT, that is a foreign key. Only the way that I specify here, and all others, no. And I want you to do maybe 10 students, department maybe 2 department, faculty maybe 4 faculties, course maybe 5 courses, enrollment maybe 15 enrollment. So you need to say some students do not enroll. That's reasonable, right? Not all students need to enroll. So 15 enrolls. So make this, and that is the homework assignments for till next week. I'm going to describe this, the homework assignments. So you don't need to worry about this. Okay? Question, Kevin?
Yeah. So for the student integer and enroll, well, that's not. So there's no foreign key. So that's not the same as the CIW, right? No, ID.
Yeah, good question. Let's make it only no primary key. So student should be, this is a foreign key from GWID. CRN is a foreign key from here. So this CRN is a primary key. This is a primary key. So primary key there, but no foreign keys. I clear that. Yeah. Yeah. I'll rewrite this clearly. Okay. All right. Good. Then we'll stop the recording.